Welcome, everybody. Thank you all for joining both the full room here in person and everybody online. And a huge thanks to family for traveling out to come be here today. So it is a sincere pleasure as Saul's advisor to give him his introduction. But before I dive into that, just as a little kind of prep for how today is going to run, Saul's going to give a 45-minute presentation where he has been tasked with the monumental task of condensing 5 years of his life into 45 minutes. And after that, we'll open it up for general questions from the audience. Usually that's about 15 minutes. After that, do you want me to kick people out or?
Nope, everybody can stay.
People stay? Okay.
Yep.
It's always up to the person. I should have asked beforehand.
That's okay.
After that, the committee gets to ask questions. You as the audience is welcome to stay, get more snacks, hang out, see that process. If you have to leave, that's also a good time to slip out before that questioning gets started. After that, we kick everybody out, then the committee deliberates, and then we let everybody back in with a decision. Cool. So I'll dive into introduction, please. Okay. So Saul did his undergraduate at University of Maryland, College Park in mechanical engineering, graduating with honors. He then spent the summer after that graduation in Cambodia doing a lot of work building low-cost robots for unexploded ordnance detection and working with 3D printing for amputees. And since coming to CMU, he's been really heavily involved, not just in research, but also in like our community activities. So he really helped revitalize MEGSO, which is the MECI graduate student organization. And he's been very involved in our STEM outreach programs. So we do a lot of outreach with like local K through 12 people. Saul was also a STEM ambassador through the Gelfand Center and has won awards for his outreach activities. So just very involved. And then somehow on top of all of that, he is also an avid rock and sometimes ice climber, and goes crazy places and does things with glass blowing. So just very impressive overall, well-rounded person. And from my perspective, the kind of cool things are robots that, no, it's all cool. Sorry, that was a bad advisor joke. So in the board, he has conducted a whole bunch of research in the space of biohybrid robotics, all the way from kind of experimental wet lab work with bioprinting through design and controls with reinforcement learning to be able to build a toolkit for future biohybrid robot design and implementation. And so I also want to just steal a moment and say a few things from myself, because Saul is only one of the kind of second cohort of my PhD students as a fairly new lab. He and Ashley, his cohort member, were in their first year thrown into COVID lockdowns and uncertainty. And Saul has been really instrumental in helping the lab navigate that, helping the lab get back up and running, and really getting the lab to where it is today. So it is my tremendous honor to introduce Saul to tell you about his research.
I really appreciate that. The title of my talk and of my dissertation is It's Alive, a toolkit for creating biological machines. And something that I think about a lot is the fact that we're so, ooh, that's not great. Something that I think about a lot is the fact that we are surrounded by spaces that are really difficult to inspect, that can be really difficult to navigate, and that can be really difficult. Interesting. Pretty severe lag going on here. Okay, really difficult to inspect and to navigate and to treat. And as a roboticist during my PhD, I've been really interested in trying to autonomously operate within these spaces. And one major source of inspiration for me is nature, and especially worms. Worms are incredibly versatile organisms that can operate at a wide range of scales and environments, from our own gardens and also in the agriculture space, to underwater, swimming around quite dexterously, as well as an inspiration for science fiction. But I'm not the only one who's inspired by worms. Other roboticists have leveraged the sort of architecture of a worm with this lattice worm approach, which shows really great promise. In this approach, the actuation mechanism, or the way that the robot is able to move, is distributed across its body structure, allowing it to contort and bend, and in this case, reach. But using sort of a very similar approach, can also generate locomotion and sort of move through the world. And so it's this distributed architecture that's really desirable. By coordinating many actuators, we can achieve these really interesting behaviors. One challenge facing robots that are made out of conventional materials is that the traditional actuators, the traditional ways of making a robot move, have difficulty being scaled down. So if these are sort of some of the ways that people can make robots move, sort of clustered by size and their force they can produce, what we notice is that beyond around 10 cubic millimeters, so around 1 centimeter cubed, there aren't a lot of ways that we can generate forces to make things move. There's just not a lot of options if we look at synthetic systems. But if we expand our approach and we look at living systems, like biohybrid actuators, then we can actually get much smaller. And so how does this work? Well, in organisms, in skeletal muscle in particular, they sort of contract in length in response to stimulus from the nervous system. And basically, you have this sort of hierarchical structure where the actin filament, here shown in purple, is ratcheted along the myosin filament. And then together, they sort of contract. And so by having a number of these units in parallel, or I should say in series, you can get really this bulk contraction that goes along. And so by using muscle tissue as an actuator, as the thing that makes a robot move, we can afford a robot with many desirable properties like self-healing that we see in nature, biocompatibility, and high compliance, all things that are really desirable for a robot to have that are otherwise quite difficult to achieve. And so researchers have been at this for quite a while. Living robots, or robots that are powered by living muscle tissue, have been demonstrated throughout the literature, showing things like inchworm locomotion, here achieved by spanning a muscle strip across a beam and then pacing its contraction to allow it to sort of inch across a dish, as well as jellyfish and ray-inspired swimming, here achieved by patterning muscles on a thin, flexible sheet, and then its contraction to sort of generate this sort of thrust through the water, as well as simple manipulation. In this case, we've got 2 muscle actuators on each side of this little finger, and by coordinating its contraction, it can achieve this sort of moving of this ring around a pillar. And this is quite significant because here we have multiple muscles and we have a behavior that's a little bit more performant. And by performant, I just mean a behavior that's more maybe useful or sophisticated or complex than, I guess, just like swimming around or twitching within a dish. And so what we see is that this trend continues. When we add more actuators, we can generate these more performant behaviors. By stitching together 2 inchworm robots, we can generate turning, right? That's what we're seeing on that left video. In the middle, we can see assisted bipedal walking. So similar, where we have multiple actuators, and with the assistance of this flotation styrofoam device at the top to stop this thing from toppling over, it's able to sort of work its way slowly across this environment, as well as fish-inspired swimming, here with muscles patterned on either side of the fish, and they can sort of trigger each other's contraction. So this is incredibly impressive work. And while impressive, biohybrid robots remain significantly less performant than their synthetic cousins, which in turn remain significantly less performant than sort of organisms we see out in the world, than like a worm in your garden or a house cat, for example. And so the question is, why is this? Why aren't biohybrid robots as performant as the animals or the synthetic soft robots that are inspired by animals? And one big reason is this phenomenon of adaptability. Adaptability is the phenomenon by which muscles get stronger through usage or strain. And we see this in our own bodies when we work out, we exercise, and we get stronger. It's really useful for organisms in that you can practice a behavior and then you can get better at it over time. But as a biohybrid roboticist, this poses a real challenge. How do we design a system around an actuator that's changing its force output with use? This is sort of a major challenge. Another challenge is there's a lack of adequate design and modeling tools for these systems. So by being able to model a biohybrid system, it can allow us to identify what shape it should be, where the actuator should be, all sort of within a computer simulation without having to build it first to understand is it going to work or not. This is incredibly important for biohybrid robotics because making them is very labor intensive and can be very expensive. And so we don't want to sort of do a trial and error approach. We want to know sort of ahead of time, to the best of our ability, is this going to work or not, and how well will it perform? So we can sort of make the whole process a lot more efficient. And so for our simulations to be sufficiently predictive of the performance of the robots that we want to build, they need to incorporate this muscle adaptability. The fact that the way that the muscle is going to produce force, or I should say the magnitude of the force it's going to produce, is going to change over time with its usage. We want that to be incorporated in our modeling tools. And so the goal of this thesis is to develop hardware and simulation tools towards achieving performant, adaptive, multi-actuator biohybrid robots. I'm just getting over a little bit of a cold. By a cold, I mean a flu. Not fun. Do not get it. And so towards this goal of my thesis, I'll be discussing 4 projects. In the first project, I developed hardware to repeatedly interrogate muscle adaptability in single actuator muscle systems. But as I sort of mentioned earlier, in animals and in sort of more sophisticated soft robots, we know that single actuators are not enough to drive performance systems. They often have multiple actuators. So in parallel, I developed a computational tool for measuring muscle adaptability in these multi-actuator contexts. Moving from measuring muscle force to leveraging it towards performant behavior, I developed a worm-inspired Lattice robot capable of simple behaviors. And then I expanded its capabilities by incorporating adaptability in its modeling and then leveraging reinforcement learning, both as a controller and as a co-design tool. So now let's begin with the hardware. So this work resulted in the submission of a patent earlier this year. And the challenge that this work tries to address, one of the challenges, is that reported biohybrid robot studies change so many important factors between them that trying to compare the muscle force output across these studies is really challenging. So what does that look like? Well, there's a lot of factors that affect the force that a muscle might produce. These are some of them. It's quite overwhelming. In one study, they might choose to use a particular cell source with a particular media composition. This is the nutrients for the robot, a particular way of making the robot, maybe bioprinting, and a particular way of getting the robot to contract. Maybe they use a very fancy optogenetic stimulation approach. In a different study, they might use a different cell source, maybe an immortalized cell line. They might use a casting approach for fabrication. They might supplement with hormones to make to get maybe greater performance in some respect. And they might opt for electrical stimulation as the modality. And furthermore, they might opt for manual handling in order to get the robot or to get the actuators to the robot. So one issue with this is that even once you make the actuators or the robots to this point, you still have to, or there's still a way that you can stimulate the robots to make them stronger over time. And so even once you've sort of adjusted for all of these different variables, there's still sort of the actual usage of the robot, which can change its force output. And if we want to build performant biohybrid robots, we need to be able to design and predict their performance ahead of time so that we can know, okay, I want this amount of force, and this is the way that I need to make my actuator to get that kind of force. And so to enable the prediction of muscle force output, we need accessible and standardized tools and methods to sort of quantify the effects of these different contributions. And so right now, the state of the art of biohybrid robot fabrication is a technique known to many of the graduate students here, and it's critical to many fields. It's known as graduate student with tweezers. Unfortunately, this technique poses a lot of challenges. Culturing muscle tissue can be extremely delicate, or cultured muscle tissue can be extremely delicate and can tear when handled. The mechanical forces imparted on muscles during handling can actually affect its force output because it can impart an unintended strain. Furthermore, it's very time consuming and requires a lot of dexterity and years to develop the particular skills involved. And then even slight tweaks of the desired muscle geometry requires an entirely new mold. And so there's sort of you often feel somewhat locked into a design once you make it. However, recent advances in bioprinting, namely fresh bioprinting, can help address some of these challenges. In fresh bioprinting, we are afforded a precise and geometrically unconstrained way of depositing muscle actuator precursors, in this case, hydrogels. So first, a bioink here shown in blue is deposited into a meltable support bath. After printing is complete, delicate muscle actuators, I should say that the support bath is gently heated to body temperature, which melts it, and then it frees up the print. And this can allow for the fabrication of delicate muscle actuators without having to touch them which, like I mentioned earlier, risks damaging them. However, once muscle actuators are fabricated, there's a challenge around trying to image them. And you need to image muscle actuators to understand the kind of forces that they're producing, as well as their maturity, sort of how developed they've become, how strong they are, how striated. There's a number of factors that are measured about muscle actuators through these imaging methods. One challenge, though, is if you're trying to image these muscle actuators, often you'll find condensation form on the top of your dish. This can obscure view of the muscle actuator. Another challenge is that often you need the optics involved require what's called like a long working distance. So the distance between like the tip of the lens or the objective that you're looking at and then the actual subject that you're trying to image has to go through this quite long path from the top of the dish through this air gap onto the top of the media, and then finally we're at the bioactuator. This can often be on the order of tens of millimeters, which is sort of a very sort of high standard to meet for a lot of objectives. And furthermore, it's really important to be able to measure these the deflection of these pillars. So as I mentioned earlier, by imaging the muscle, we can actually figure out what kind of force it's producing. Bigger force, more pillar deflection. And so it's important to be able to see these pillars quite clearly in order to understand the effects of these different factors I mentioned on the force that the muscle produces. And so one way of getting around this issue of having challenges with long working distances imaging from above, or challenges trying to image from below, which is often blocked by the sort of substrate that the muscle is cultured on in the first place, is by imaging from the side. So normally, the optical path, or the path that the light would take, comes from the bottom of the microscope through your sample and then up through the sort of optics up to your sensor. In the approach that I'm pioneering, we just rotate the whole microscope, and instead, we can actually see through the side of the sample that we're looking at, and then we can sort of eliminate a number of these issues. So the optical distortions due to condensation are no longer a concern because we're sort of imaging from the side. There isn't sort of a top issue. Challenges of long working distances are addressed because we can make our dish relatively thin, and that way we can sort of fit it within existing microscopes. And then also we can get a clearer view of where the tissue is on the pillar because we're looking at the side, and that sort of critical metric of how far has the pillar deflected is a little bit easier to measure. And so this is great, but existing culture dishes, like the plastic that people would do this sort of experiment in, are not suitable for lateral imaging. So I created a lateral imaging and fabrication with electrostimulation, or LIFE vessel, that addresses these challenges. To address challenges in imaging, I introduced this biofabrication chamber that's compatible with lateral imaging as well as fresh printing. I also introduced, or rather I developed an ad hoc electrical stimulation approach that hopefully, or that whose goal is to standardize the electrical stimulation, which is often sort of ad hoc in many previously reported studies. And to address challenges associated with the graduate student with tweezers technique, I integrated automated fresh bioprinting for the deposition of the muscle actuators onto these pillared scaffolds. And so what we want from this dish is for it to be flat, or to feature flat and transparent walls so that it can be compatible with lateral imaging. We want these walls to be tall so that it can contain both the scaffold, the muscle actuator, and then sort of sufficient media on top of it so the whole thing can be submerged, as well as a sort of an air gap layer. And it needs to have a thin profile so it can fit within existing microscopes. So now I'm going to talk through each of the subcomponents of the system, starting with this biofabrication and sort of bioreactor chamber. It's made of this vacuum formed PET sheet, costs on the order of cents. And the way we vacuum form is first we take a sheet here shown in red, we heat it up, and then we have sort of this mold known as a buck. We pull it down over the mold, and then we pull a vacuum, and the 2D sheet now conforms to this 3D shape. We release the vacuum and then can lift the part off of the mold. And in that way, we can sort of capture the shape. Excuse me. So the next subcomponent is the electrical subsystem. And for this, I worked with Reagan Kupicek, a colleague in the mechanical engineering department. I designed I specified the electrical requirements, and then he designed the wonderful box that allows us to sort of meet these requirements. And so what this box does essentially is allow us to, excuse me, it allows us to take an input DC voltage feed it into this relatively or extremely low cost system, and then output a square wave where we can specify the pulse width as well as the frequency and the duration of the stimulation, which are sort of the key factors that people normally want to, the key knobs on electrical stimulation that people mess with when they're stimulating muscle tissue. Furthermore, it allows a user to change all of these different features with just that little knob in the middle. So you don't have to know anything about programming in order to change this system. Hopefully that feature allows it to be democratized more broadly. Furthermore, this, as I mentioned, the system is made up of pretty inexpensive and readily accessible components. So we have like a $50 power supply, off-the-shelf microcontroller, a display, and sort of all of these together allow for the stimulation that are compatible with this life vessel. And so by integrating all of these subsystems together, we're able to use this fresh bioprinting method. Here I'm showing an earlier iteration of the life vessel, but we can deposit sort of a hydrogel around these pillars. It's sort of shown in this ghostly white. And with a single press of the button, it can deposit one bioactuator and then queue up an index to the next location, and then autonomously or sort of automatically with another click of the button, deposit a second bioactuator and then get out of the way. And so altogether, the life vessel can standardize the characterization of bioprinted muscle actuators. It exists as a single dish platform that enables lateral imaging, fabrication via fresh bioprinting, as well as electrical stimulation. It's comprised of off-the-shelf components, and it's very easy to assemble. And so altogether, this physical platform enables researchers to interrogate the relationship between fabrication and stimulation parameters for single muscle tissues and their force output, which is, again, very critical for them to accomplish operational tasks outside of the lab. However, like I mentioned earlier, in animals and in many robotic systems, single actuators are not enough to drive performant behaviors. And so to this point, this next chapter outlines a computational approach for interrogating the relationship between mechanical stimulation history, so that's like stretching, and muscle actuator force output in these multi-actuator, so known as distributed architectures. So this work resulted in a peer-reviewed publication, as well as a poster session, no, actually a podium talk at the Living Machines conference in 2022. And the motivation for this work is the motivation for a lot of what I talk about in this presentation, is this muscle actuator adaptability, right? The fact that it's this double-edged sword. Muscles that experience strain can get stronger as a result. And this relationship is poorly understood in biohybrid robots, especially in these distributed contexts where different muscles can pull on each other and sort of induce strain in each other. And so this poor understanding has led to sort of a lack of design and analysis tools for these more complex multi-actuator biohybrid robots, which has led to the state of the art being these relatively low degree of freedom, but really impressive lab-tethered research devices. So what we have are these really incredible potential for what biohybrid systems can do, but we have these really simple devices. But we want more complex devices. Why do we want that? Well, because a distributed actuation biohybrid robot could have this really incredible potential. We can imagine having a trainable and behaviorally flexible biocompatible system that can adapt to sort of changing or dynamic environments in vivo inside of our body, with really incredible applications, potentially long-term in medical robotics. We can imagine having stents, endoscopes, or tools for minimally invasive surgery. This is very laudable. I hope we get there one day, but we're quite far from it. In the short term, however, this distributed mesh-based biohybrid architectures, like the illustration shown here, are a really useful platform to study this sort of distributed muscle actuation adaptability to sort of hopefully get us to those long-term approaches in the future. And so the motivation for this work, right, is that we need tools for distributed biohybrid actuation systems. We need them to be able to estimate muscle strain, and we need them to estimate muscle force. We need these tools to be accurate, right? They need to sort of represent and to model reality. We need them to be computationally inexpensive. We want to be able to use them as part of our design loop, and so they take a long time to compute. That makes it a little bit more challenging. And we need them to be contactless. Muscles are very fragile, as I mentioned, or cultured muscles can be very fragile and challenging to move, and the contact forces from touching them can sort of impart unwanted strain. The roadmap for this section is that first I'll be talking about a technique I developed for estimating muscle strain on a substrate that's being stretched, as well as two methods for estimating muscle forces when that substrate is not being stretched and all the deformation is because the muscles are sort of tweaking it. In the first method, the response surface optimization method, the two methods are rather the response surface optimization method and as well as the direct optimization method. And in all cases, we're looking at this 2D mesh system. We have a mesh substrate. On it, we pattern muscles here represented as springs. And we subject, for the stretching, we subject that system to some stretching exercise. We can fix the top and the bottom so they don't move, and then subject the sides to stretching, and we can measure the muscle strain. And then for force transduction, for measuring force, we fix all of the edges, and then we're just looking at the deformation of the mesh under the action of the muscles. So first on to sort of estimating muscle actuator strain, which again will influence muscle actuator force. A key question to ask is, what do muscles experience when they're on something that's being stretched? And it's important to note that the thing that's being stretched, like what the mesh experiences, is not the same thing as what the muscle experiences, because it depends on a number of factors. What is the orientation of the muscle with respect to the stretch direction? Is it aligned with the stretch direction? Is it perpendicular? And where is the muscle on the mesh? Is it near the center of the mesh? Is it near the edge? These sort of impact the kind of strain a muscle might experience given the same like displacement on a mesh. So to measure muscle strain on a mesh, we have again this mesh substrate, and we pattern on it these virtual muscle strain gauges that will report back the kind of strain a muscle might experience if it was patterned in a particular location. The way we get that strain is by looking at where the muscle is attached to this mesh. And what we want to know is, in any orientation or location, what kind of strains might be experienced. So we track these sort of 12 nodes to get a description of the kind of strain a muscle might experience. So equipped with this tool, what do we find? Well, here's what we find. Unsurprisingly, when the muscle is aligned with the direction of stretch, that is the case that results in the maximum strain. On this plot on the x-axis, we have the stretch. Positive values are in tension, negative values are sort of in compression. So the case that we're looking at right here, this video, is this peak right here. And so this is fantastic. We now have a tool that can report to us what kind of strain muscles are experiencing when they're on a mesh that's being stretched. So now we can move on and try to figure out what kind of forces the muscles are producing maybe before and after they're subjected to this sort of stretching. And so this gets us into our force estimation tools. For these distributed muscle force estimations, our goal here is, again, we're looking at this fixed mesh, and then it's got muscles patterned on it. The muscles are contracting, and they're making the mesh move. What we want to do is relate that movement, that mesh deformation, to the forces that cause the mesh to move. So again, we got a mesh deformation. We want to feed it into some computational model, and we want it to tell us what were the forces. One approach that we took is using this response surface optimization method. You're about to see a big chart. Don't worry, I'll break it down. Okay, so basically what we do is we want to create a mapping between the forces that muscles produce and the kinds of deformations on the mesh that happen. That's what's going on in the yellow box. We want to know, is this mapping going to be good for us? And we want to search on that mapping such that if I input a mesh deformation, I can get out a muscle force. So we're going to generate some sort of test mesh deformations. We're going to feed it into our estimator. It's going to search on this continuous surface that we've generated, known as the response surface. And it's going to give us an estimation for the muscle forces that it estimates were produced, or rather that produced this input mesh deformation. And so we can take sort of the difference between the muscle force estimation and the ground truth of the muscle forces, and we can get out our method error. So how do we do? Well, if we train sort of this response surface on 200 muscle force input sets, we test it on 10 muscle force validation sets for this force range, we do okay. Our error is not an insignificant chunk of our range, and our max error is around 11% of our range. So this is okay, but it doesn't quite meet our criteria for having an accurate tool that's like reflective of reality. So that motivated us to look at a different approach for estimating these muscle forces. This is the direct optimization approach. Again, another chart, but you're in good hands. So in this approach, instead of generating a response surface, which is very computationally intensive upfront, we repeatedly solve a simulation using the finite element method to figure out what is a better guess for the muscle forces that produced an input mesh deformation. So again, we still have an estimator, but in this case, we're performing a finite element analysis iteratively, which is computationally expensive. But we still have our testing data, we're generating these mesh deformations as ground truth. We're still feeding them into our estimator, and then we're still producing these muscle force estimations and comparing it to our ground truth. So in this case, how do we do? Well, we do quite well. We actually get 0 error. You say, Saul, 0 error. I don't like the sound of that. That's too low. It's too good. This isn't quite surprising because we can iteratively update our estimations until we converge on the exact solution. The fact that we can perform the finite element analysis iteratively means that we can actually get to 0 error. So there's a whole lot of sort of word salad. But basically what I said was, it's not too different than if you take a math test and then every time you think you have the right answer, you can raise your hand and show the teacher and say, hey, was I close? And they give you like a yes or no and point you in the right direction. You do that infinitely many times, not infinitely, but many times, I hope you get to 0 error. And so that's basically what we have here. So to truly assess the performance of this approach would require experimental validation. And so let's compare sort of the trade-off between these two methods. In the first method, we have to generate this response surface. It's a lot of compute, a lot of sort of computationally expensive upfront. And for the direct optimization, there's sort of no uptime or no sort of, you don't have to do that is what I should say. For the time it takes to estimate a given muscle force set, the first method takes around the order of a minute, right? So for that compute you outlaid up front, you can do fast estimations. For the second approach, it takes around 10 times longer, so it takes around 10 minutes. And then for the first method, we're getting this sort of somewhat poor accuracy. For the second method, we're getting quite high accuracy, but again, both of these sort of need to be validated with a physical system to truly assess their performance. And so altogether, the technical contributions of this chapter are a contactless method for estimating muscle strains on a stretched mesh, as well as 2 contactless methods for estimating muscle forces. One that is fast but imprecise, so the response surface method, and one that's slow and precise. This is the direct optimization method. And so together, these contributions support the interrogation of muscle adaptability, specifically muscle strain and muscle force in these distributed multi-actuator contexts, which are critical for developing these more performant biohybrid robots. And in the next 2 projects, I extend my work beyond measurement to designing, modeling, and controlling distributed muscle-driven robots towards these performant behaviors. And this is necessary because current biohybrid robots are single function. They're remarkable in what they're able to achieve, but they can only do one thing per architecture. And this is by dint of the fact that they only have 1 or maybe 2 actuators that drive them. Organisms, by contrast, have many actuators and it can accomplish many things, right? So like my hand and yours, hopefully, has many muscles, and together you can coordinate simple actions that when you string them together can sort of generate more complex behaviors like throwing your water bottle around or writing or other useful things. And so that's sort of the goal here, is to move from these single actuator or couple actuator systems to many actuator systems. And this work resulted in the publication of a peer-reviewed article and a poster session at the 2023 Living Machines Conference in Italy, as it happened. That was pretty fun. So yeah, the goal, as I mentioned, of this work is to develop an architecture that is able to achieve multifunctional behavior by demonstrating motion primitives first. These are the simple behaviors that you combine together and get more complex behaviors. The tool that I used for this is called PyElastica, which is a Python implementation of a validated biohybrid design tool. So here, we've got a little inchworm robot. It's driven by the simulated muscle actuator. And then here, they made it. It's driven by a living muscle actuator. And so they're able to sort of predict the performance of the thing that they made by simulating it. That is exactly what we want our simulation tools to do, among other things. What you'll notice here is that what we're dealing with is a relatively simple biohybrid architecture. And one reason for that, excuse me, is that it's really difficult to make more complicated architectures in Pielastica. So for the mechanical engineers in the room, you're probably familiar with SolidWorks or Creo or Autodesk Inventor. There's no such luxury in Pielastica. Everything is written as a line of Python. So if you want to design more complicated structures, it's a real headache. And so I designed a tool to make that a little bit easier. This parametric method for creating lattice form architectures allows a user to input these sort of like broad metrics that they want for their resulting lattice form, the height, the width, the number of muscles, where they're placed, and it will automatically generate sort of a Pielastica compatible model that you can sort of simulate its performance. This is really powerful because what it allows us to do is test like what sort of basic motions can I achieve with a robot with this architecture, but I didn't have to build anything. And so what I was able to achieve is 3 sort of basic motion primitives. In one case, extension by coordinating the contraction of muscles that are sort of patterned circumferentially around this robot, as well as compression. Here, longitudinal muscles drive the whole system to compress, as well as bending. So here we've got both longitudinally patterned and circumferentially patterned muscles that are done strategically so we can generate this bending behavior. And the metrics on this are pretty good. I can get 50% taller, about 30%, I can achieve 30% compression, and I can achieve more than a 45-degree bend angle. So we're very, excuse me, very happy with this performance. But one thing to note is it's still limited, right? Motion primitives are not the same thing as performant behaviors. The adaptation of muscle actuators to use history, which is something I've been harping on this whole talk, was not captured in this sort of first pass at trying to create this architecture. And so that's sort of the motivation for the 2.0 version of this work. How do we effectively design and model distributed actuation systems whose performance changes with use? So that's the subject of the next and final chapter of my thesis, which is this distributed biohybrid design and control approach, which is currently in preparation. The title hopefully will be Hitting the Gym, Reinforcement Learning, Control of Exercise Strength in Biohybrid Robots. So the modeling needs for this sort of upgrade is that we need more muscles. Always we need more muscles. We need more muscles for better performance, but it's sort of like adaptability in that it sort of comes at a cost. It's a double-edged sword. We upgrade from 6 to 42 muscles. That's wonderful. Now we have to coordinate the contraction of 42 different muscles. We probably don't want to contract them all at once. So we want our modeling tool to help us coordinate these contractions for us. Furthermore, biohybrid actuators are really expensive. So great, you got a biohybrid robot, you put 42 muscles on it, but did you really need every one of those muscles? Was that strictly necessary? So we want our tool to tell us which muscles are actually being used to accomplish a task, so we don't have to go through the arduous and very expensive application process for actuators that aren't actually contributing to performant behavior. Furthermore, if you wanted to do this sort of like iteratively or like through an Edisonian process, let's say we wanted to only pattern 20 muscles. We have 42 different places that we could pattern them. There's actually 513 billion ways that you could do that. So we really need a computational tool that can tell us, because this actually ends up being a combinatorically hard problem to solve. And finally, we want to be able to identify or prescribe, I should say, what we want the goal of the system to be. So we want to be able to simulate the performance of this robot accomplishing a specific goal. Right behind this video is a little green dot. And so this is sort of the target for reaching. This is the performant behavior I've selected for this study. And furthermore, we want this model to capture adaptation in response to use, because we know that this is so important to the actual behavior of living muscle tissues outside of simulation, out in the real world and in our petri dishes. So I selected reinforcement learning, both as a co-design tool and a controller to help me tackle some of these issues. How does this work? Well, in reinforcement learning, we have an agent. Here is our little robot. It takes an action which can operate within an environment. The environment in our case is our Pielastica simulation environment, where we have this structure that has this sort of lattice shown in purple, and it's got muscles, 42 muscles that are patterned in all of the sort of potential locations you can have a muscle on the structure. And it gets a reward for coordinating the contraction of these muscles towards a specific location. So I've got 8 target locations 4 of them are at the top. They're a little bit further away. These are targets 1 through 4. And 4 are a little bit easier. They're near the bottom. These are targets 5 through 8. And the agent can take observations or is provided observations about this environment, namely the location or sort of a description of the location of this robot in space, as well as a description of where the target is in space, as well as how fast the robot is moving. And it gets a reward for closing that gap between where the robot is and where the target is. And so this is particularly desirable for us because in reinforcement learning, the agent learns iteratively. So it will make some decision about how it thinks it should move the robot, it'll run the simulation, and then it'll get some feedback about how close was I. And so what we can do is between episodes, we can say, hey, you used that muscle in a previous episode. Now it can be stronger. And so in this way, we can incorporate adaptation directly into our modeling tool by using reinforcement learning and changing the performance of the muscles based on their usage in previous episodes. Reinforcement learning here is used as a controller because it is contracting, it's coordinating the contraction of different muscles in order to achieve the goal. And it's being used as a design tool because it can help us identify which muscles are actually needed to reach to that goal. And we only have to make those muscles, as well as modeling the adaptation of the muscles that are actually being used. And so how do we model that adaptation? Well, in my implementation, I've modeled muscle actuation or muscle actuator adaptation using 3 key rules. Rule 1, reinforcement learning agent is going to select the activation intensity of a muscle. Okay, great. Rule 2, muscles that are stretching or that are producing force in a given episode will experience adaptation and get stronger. And then rule 3, muscles can't get more than twice as strong as when they initially started. So you don't have muscles that are totally yoked out. So let's formalize this a little bit more mathematically. What does that look like? Well, for a given muscle in a given episode, the force that it produces is equal to the activation selected by the RL agent for that muscle at that episode, times the force ceiling of that muscle. This is the value that changes dependent on usage history. That force ceiling, in turn, is dependent on the adaptation of that muscle times the force ceiling of the previous episode. So it sort of updates the force ceiling based on its previous force ceiling. And then that value is capped at being no more than twice the initial force ceiling value. That adaptation, in turn, is dependent on the strain of the muscle in the previous episode. So how much was it stretched or contracted, as well as the force that it produced. So was the muscle even used in the previous episode at all? So this creates a whole lot of math, but again, you're in great hands. What does this all mean? The force ceiling depends on strain, or the force ceiling for a given muscle depends on the strain and the usage history of that muscle in the previous episodes. And so in this way, you can sort of capture adaptation. So what we want to know is how does a system that incorporates adaptation perform compared to one that doesn't? Is a reinforcement learning agent going to have a harder time learning a system where muscles are changing over time? Is it going to perform better because the muscles can get stronger? We have to design an experiment for that. So that's what I did. We got 2 environments, one where muscles can get stronger and an identical one where they can't get stronger. Again, both of these environments are the case where we have our lattice worm and it's reaching towards a target location. I changed the target location. So we've got 8 potential targets that the agent can try to learn. And we do it for 5 seeds, sort of compare and see if the initial seeding of the policy network was a large factor. We don't want that to be a factor. So we submit these as batch jobs to our high performance computing cluster. This is basically a supercomputer that I'm very lucky to have access to. And it does a lot of computing and then tells us, how did we do? Basically, what we get out of this big computation is a description of the adaptation of these muscles and the learning, I should say, of these agents across 8,500 episodes. So in the first episode, agent isn't very good at the task. Hopefully by episode 8,500, it's a lot better. 8,500 sounds like a big number, but in the context of reinforcement learning, it's usually around like tens of millions. So we're actually going pretty fast here, which is great. And so what do we learn from all this computation? Well, we can identify achievable goals and associated controllers for our system. So I can prescribe a location that I want to reach to, and I can train the RL agent to try to coordinate the muscles to reach there. And if it's able to do it, I know that it's actually possible for this system to achieve that goal. And if it can't, maybe it's not possible. So this is very useful because I can identify ahead of time what is possible and what isn't, just through simulation. Another thing we can learn is we can identify which muscles are required for a given task based on their activation intensity. So if I unwrap my lattice worm and I highlight which muscles are being used based on how red they are, we can see that actually not all of the muscles are being used. This is really important to know. And then finally, we can model this adaptation and we can interrogate it across many episodes. This is a chart I will describe in a little bit. So what happens when we model these distributed actuation adapting biohybrid robots and we deploy reinforcement learning to learn a control policy? Well, we are able to achieve targeted reaching. So here the goal is to sort of just touch this green dot by coordinating these muscles, and we're able to do so. So, all right, perfect.
Yeah.
You're excited, it works, but how does it work? How well does it work? Specifically, what does it look like as it's learning? So what we find is initially when it's learning, it's not doing a great job. It hasn't really quite figured out what we're doing here yet. Okay, how about later on learning? All right, oh, it's okay, now we're signing in a different direction. So, okay, it's hard, we really do need these 8,500 episodes, it seems. Yes, thank you. So what is being passed back is a description of a successful control policy that has moved directly from Pyelastica through the magic of Python foo into a 3D printable plastic part that sort of demonstrates in different stages one sort of gross reaching behavior, one bulk reaching behavior. Okay, and finally, so I've walked you through initial learning, through a little bit later in the learning process. What happens at the end of learning? Boom, we can sort of bullet to the location that we want. We're very directed, very happy. Okay, so this is great. Additionally, as muscles are used, and this is expected, in the adaptive environment case, we see that the muscle force output is increasing. So this plot has a lot going on. I'm going to walk you through it. Each pink dot represents the muscle force of a specific muscle, in this case, muscle 18, in a given episode. You say, Saul, I see pink dots and pink lines. The pink lines are many, many dots that are very close together in value. So they sort of blur into a line. We're also seeing blue dots, or really a blue line. This is the force ceiling. So this is the maximum force a muscle could have produced in a given episode. And so what we see is when muscles are being used, let me get this mouse over here. When muscles are not being used, that is when their forces are usually tending around 0, we see that their force ceiling is not increasing. Great, that's exactly what we'd expect to see. When the muscle starts being used more, when you're hearing this overlap between the muscle force and the maximum that it can produce, we see that the force ceiling is increasing. Perfect, that's adaptation in action. And then finally, I've lost the mouse. Oh, there it is. Okay, finally, when the muscle, if the muscle is no longer being used, then the force ceiling will plateau. This is excellent. This is exactly what we want to see. And furthermore, if we look at a different muscle, we see that if it's being used constantly, let's say this is a very important muscle, that its force ceiling will plateau at a certain point at twice its initial value. So great, we have successfully implemented adaptation and it's behaving in a way that we expect. And so in this way, I've been able to capture the use history of muscles as part of this holistic model that integrates biohybrid robot adaptation with this episodic usage approach. So how do we do when we're trying to reach to specific targets? Well, if we're looking at target 1, if we look at the adaptable case, what we find is we're doing pretty good. We get like pretty directed reaching. Target 1's kind of hard, it's pretty far away. So we're not quite there, but we're pretty close. This is a little bit outside of the workspace of the robot. What about for the non-adaptable agent? Okay, well, we're doing all right, but it's just not as good. And the reason for this is the fact that the muscles just can't generate the requisite force to just get there, right? They're hamstrung by the fact that they're not adapting. How about for the easier targets? So this is corner 6, this is a little bit lower. Wow, ain't that beautiful? That worked great. It really got there. How about for the non-adaptable agent? Man, just a little bit weaker. Right, so what we're seeing, we see this sort of trend for both corner 1 and corner 8, right? So for the higher, harder target and the lower target, there's sort of a bigger performance gap for the higher targets, I should say harder targets. Here, the red line represents the performance of the system when it's operating in an adaptive environment. And then the blue line is when the environment is non-adaptive. And so what we see is consistently, sort of across the board, the agent is able to learn a policy that is either on par or exceeding the performance of the non-adaptable agent. You say, Saul, that's kind of weird, because earlier you said, I remember this, you said that having a policy where the muscles are changing between episodes would be harder to learn. So how is it that it's able to learn either a successful policy that's on par or better? I think that this is because the way I've implemented adaptation is an instance of curriculum learning. Curriculum learning and reinforcement learning is basically when you give your agent a somewhat easier version of the problem that you want it to solve, and then over the course of training, you make that problem a little bit harder. So it learns an initial policy that's successful for an easier problem, and you ramp up the difficulty, and it can sort of just modify that policy a little bit and get to a higher reward. And so that's sort of my hypothesis about why this is working out so well. So to more easily sort of compare the performance between these agents across these sort of 8 different reaching tasks, we can look at the maximum performance. So in a given, for the whole training, what was the best episode? And then average it across all of our different seeds. And we see across the board, the adaptive agent that does better, which we attribute both to curriculum learning and to the fact that it can muster greater forces through adaptation. And that effect is, or that sort of difference is larger for the harder corners. So this is corners 1 through 4, than for the easier corners. This is corners 5 through 8. So one thing that's really exciting to me, beyond the fact that this worked, is the fact that it came up with a control policy that I didn't intuitively ever think about. So in all the videos I've shown you, we're sort of reaching, we're sort of closing, there's sort of a convergence happening at the top of the robot. But this agent had a different idea. In this case, there's a splaying out at the top in order to sort of maximize the reward. And that's because that one particular point, which you can see right here, is the point that's actually being tracked for the reward. So the agent is able to discover a control policy that the designer didn't intuitively think of, which is very exciting as a designer, because now I've got sort of like a friend in the computer that's giving me suggestions about how I can accomplish these tasks. And so the technical contributions for this project are, first, I upgraded from 6 muscles to 42 muscles. I implemented this bio-inspired muscle adaptation scheme. I am able to identify muscles key to task completion. I leveraged reinforcement learning both as a controller and as a co-design tool. And then I developed a number of visualizations for biohybrid design. So all the pretty visuals are for me. They're not sort of native to the tool that I'm using. And so the conclusions of my thesis are that in the first chapter, I detailed the life vessel, which is here. And it allows for the interrogation of bioprinted muscle actuators, helping to parse the effects of these myriad factors that influence muscle force output. In the second chapter, I developed a contactless optimization-based suite of tools that allow for me to estimate these key parameters governing muscle actuator adaptation, namely muscle strain and muscle force, using the finite element methods, and then coupled with these multi-objective genetic algorithms. And then building from this work, I developed this 3D biohybrid design and control tool, first as a concept prototype with 6 muscles and 3 motion primitives. And then I expanded this work leveraging 42 muscles, or upgrading, I should say, to 42 muscles, leveraging reinforcement learning both as a controller and as a co-design tool, implementing muscle adaptation and achieving this performance reaching behavior. And so building biohybrid approaches can drive adaptable solutions to hard problems. And this work lays the foundation for a world in which researchers and engineers can build robots to operate in diverse environments with living materials like muscle tissues. And being able to measure, design, control many actuator systems, these muscle-driven systems, can push the field of biohybrid robotics towards these more performant systems that can operate outside of the lab. My work has resulted in a number of publications. So here are my first author peer-reviewed publications, and I've got one sort of in the pipeline. It's going to go out next week. My work has also resulted in a patent submission, as well as 2 co-authored publications, and then another co-authored publication that's in preparation. I'd like to acknowledge my wonderful lab. You guys have been fantastic. Couldn't have done it without you, really. As well, that's my even more wonderful funding sources. Without whose money, none of this was possible. To the NSF. And then I have one last muscle-driven robot to show you. It's me. This is a motion capture video of me dancing, provided by the resources of Anna Bales's lab. Thank you so much. And I'd like to thank a number of folks. Thank you to Victoria Webster Wood for hiring me 5 years ago when I was just a scrappy young undergrad and providing the greatest mentorship a young scientist could hope to have. Victoria Webster Wood is not only a brilliant scientist and engineer, she is a brilliant person who cares deeply for all that are graced by her tutelage and mentorship.
Woohoo!
Each of these can be hard at times, but working with Vicky is always joyous. Thank you. Emily, especially during hard times, my parents, my sisters, my grandparents have always been in my corner cheering for me. Thank you.
Woohoo!
I have my partner, Anna Bales, from our rock climbing adventures in Yosemite to side-by-side riding sessions next to your wonderful dog, Luna. I am so lucky to have your love and support. Thank you for listening to this presentation countless times and in countless forms. Thank you for spending a Saturday morning with me to get these motion capture videos. I can't wait for our next great adventure. To my friends on person and in Zoom. I am so honored to have friends from all the stages of my life since high school here to support me. People sometimes say that graduate school isn't supposed to be fun, but together I think we've proved them wrong. Thank you to all of my professors, both from undergrad and grad school. You not only taught me technical skills, but inspired me to become an engineer and a scientist. And finally, thank you to my high school teachers, many of whom are here on Zoom. The skills I learned from you in courses from English literature, physics, anthropology, and calculus are cornerstones of my intellectual development. They are the tree, the foundational structure upon which I have hung all subsequent knowledge I have gained in the decades since, and you are all pivotal to my development as a human being, as a scientist. Thank you. I did get a biohybrid robot to do the worm. And on that note, I'd like to open the floor to questions. Thank you.
So we'll start with questions from the audience.
Mitch.
Saul, great talk. I loved it.
Thanks.
Can you go to the slides about direct optimization?
Yeah.
And I had a question on what, if any, is your initial seed for your mesh? And could you use both methods, the fast but inaccurate one, to come up with a better initial guess for your first finite element method, since it's iterating over that mesh over time?
Yes, so that's a great question. The seed is currently randomized, and we could have a hybrid approach where we can take some of the insights from the response surface method, right, where we can get a sort of initial guess that's really quick, and then we could feed that into the first guess, so that maybe where before the direct optimization method takes maybe on the order of a minute, or I should say on the order of 10 minutes, maybe we can bring that down by an order of, by a factor of 2 or something, get it down to 5 minutes by bisecting the space that we're searching by having a better initial guess. Great suggestion.
And then, sorry, I had a second question.
Please, more questions, better.
My other question was, what is your actual reward for your learning agent?
Yes, so the actual reward for the learning agent is the distance squared plus a factor that is added on. It's a negative of the distance squared plus a factor that's added on if it reaches, I think, within 5 millimeters and then within 1 millimeter of the target. So it's sort of staged.
The other thing I think I was questioning, I think you have the inverse of curriculum learning because your muscles are becoming stronger over time. And so the problem becomes easier rather than harder. So I wonder if you know, what are your thoughts on that?
Yes, so this is a very good point. I forgot to mention a key detail. If the muscles get too strong, they can destabilize the simulation and rip it apart, which leads to a immediate reward that is like quite low compared to what it could have achieved, which is difficult for the agent to learn from. And so it's easier to, I guess, learn a policy where the muscles are small because they don't destabilize the simulation, but then the performance that you can achieve is lower. So you could decrease the time step so that you don't destabilize your simulation, but then your compute time goes up. So it's sort of this big trade-off. But yes, the reward, the problem gets harder because now the agent can destabilize the simulation and then basically waste a training. I feel like my understanding is that its knowledge gained from a simulation that's destabilized is less than a knowledge that just isn't as performant.
Thank you.
Thank you. More questions?
Just wondering.
Aaron, please.
Can you use the scatter chart?
Sorry,
The scatter plots?
can you tell me what section that
With
was?
the
in?
muscles.
The muscle.
Oh, got it. Yeah.
You know.
Yeah. Okay, great.
So am I correct in understanding it's like at the force ceiling for most of the fact
Yes,
that it's,
for muscle 41, it's at the force ceiling basically the entire time.
so is that like optimal resource usage, or are you worried that you could like injure the muscle by being at the
Great
max?
question. So my model does not incorporate a number of factors that future models hopefully will for biohybrid robots, like fatigue is one of them, and also I guess like damage to the muscle through use. So people, when they work out, they often feel sore. It's because they've done physical damage to their muscles, and that's one of the mechanisms that allows them to become stronger. This is not captured in the muscle. So very good insight that we would want to maybe have a penalization if you're using muscles in maybe subsequent episodes and not allowing them to get rest and then maybe repair. So in a future version of this.
Do you have a sense of what the like, I don't know, RPE or like what the exertion is that you want is the optimal?
We would want to use something like the life vessel in order to understand what sort of like magnitude of activation is responsible for causing damage, and then maybe operate below, let's say like an 80%, like, maximum oomph.
Cool.
Thanks. More questions? Please ask questions. We got Nathan in the back.
This is a really good segue to my question, or one of my
Sweet,
questions,
yeah.
which was, I know that we talked a lot about adaptability in terms of strengthening the muscles, but something else that I often think about is like muscle atrophy.
Yeah.
I
Absolutely.
don't know if you have thoughts on like how that would have changed results if you allowed the model to incorporate atrophy, for like example with the muscle 18 chart, where it
Oh,
seems to
yeah.
raise its strength.
Maybe like
and then
this value over here.
starts to use the muscle less because its strength ceiling is now much higher. But do you think that things would be rendered, I guess, either more optimal, but maybe more complicated if there was some allowance for the muscle strength to start to decrease as it gets used less?
Yeah, and that's a great question. I think that the reinforcement learning agent would still be able to learn a control policy where there is like a decrease if the previous episode did not use it. I think that if we want to design a robotic system that is actually capturing the mechanics we see out in the real world, we would want to incorporate that. One sort of intuition that I have about the nature of the problem is that muscle growth, or like muscle adaptation in the positive sense, would happen at a shorter time scale maybe than muscle atrophy. And so it's possible that the time that it takes to train a robot is on the order of like maybe a week, where the time for the robot to like atrophy for lack of use is maybe on the order of a couple of weeks. But it's, I would imagine, hyper dependent on like the cell source and the stimulation parameters and like the composition of the media. So this is a great question for like further investigation of like experimental biohybrid actuator studies. It's a really good insight.
I have a follow-up question
Please.
as well.
Yeah.
Okay. I guess I was gonna also ask, do you think that adding sequencing to your like training would have any changes on the muscles that get utilized versus not? So for example, if your robot is tasked with reaching to like the top corner and then now moving to a bottom corner,
Yeah.
do you think that that would illuminate different results about useful muscles as far as getting from different point A to a different point B.
Absolutely, yeah. I think that we can start to learn a lot about if we wanted to deploy a robot that's multifunctional and performant, so it can do a couple of things that are useful, then that's exactly what we would do. We would train it to do these different tasks. And then that could tell us which muscles are useful. So yes, I really do think that that would be helpful.
That was my follow-up.
Question about when you have those models that go sideways, you want to, the bending ones?
This one,
Yeah, so you were saying at the bottom here, the ones at the the muscles, I guess, or actuators at the bottom don't have to work as hard. They're not being used as much, but they are being used a lot at the top.
oh, when the target is to reach targets near the bottom, so targets 5 through 8,
Yes.
those are closer to the robot starting position. So actually, this is a little bit clearer on this side. So if we look here, notice how the green dot moved down.
Yes.
Now it's actually easier for the robot to get there because it's actually closer to its starting position. So in this case, corner 6 versus corner 1,
Right.
the muscles across the whole robot don't have to work as hard.
Is there any way that stuff that's not working as hard, that power that's not working as hard goes into something else? Again, I'm not a scientist.
Yeah, no, for sure. Yeah, the fact that we can identify which muscles aren't being used means that we can save our resources for those that are, right? In terms of our media, the glucose in the media, maybe if this is in an environment without oxygen, the oxygen that's been perfused with the media. Yeah, so the intuition that you have of like, how do we better, more efficiently use our resources that are limited are absolutely sort of captured, and we can sort of redistribute those. Michael, in the back. Oh, yeah, I guess after you is the last question.
First of all, really great talk, really well communicated, really appreciated getting to watch through this. Kind of building off of those previous questions.
Yeah.
One thing I was curious about was you have that data on the muscles that really aren't being used too much throughout their time here. Have you tested models where you essentially removed those structures out of the structure? Because I'm curious to know if you can get away with removing those, and that might make things easier in production and process of creating the actual structure, or if those are providing some kind of structural benefit that isn't captured well just from not it being used to generate force.
It's a very good insight. I have not looked into that, but certainly is great fodder for the next PhD student. I'm gonna insist that we do 2 more questions. So Michael and then Peter.
I was gonna use the kind of classic Saul questions. What was kind of the most rewarding aspect of all this work? And if you were to kind of like start from scratch and having this knowledge base now out in the world, where would you like want to go next with this?
Great question. The most rewarding thing from my work is this slide. This was one of the earliest slides where I saw the performance of my robot after successfully learning a control policy, and to see it, oopsie, not that part. And to see it just like so wackily learn a policy where I was like, what are you even doing? That was joyous. So this was probably the highlight. I think there's a lot of recency bias because this happened just a few weeks ago. So that was a big highlight. And then what would I do equipped with this knowledge? Well, I think a lot of the questions that people asked are like questions that I've been thinking about of like what I could do if I had like another PhD ahead of me. But I think I would really love to integrate this with the life vessel as well, and really close the loop on testing what kind of forces we think we can produce, trying to sort of predict what kind of forces these muscles can produce, and then actually fabricating systems to achieve these behaviors. So we know like we're actually modeling something that's reflective of reality. And then final question, Peter.
Thank you. First, Michael, that was my question. You actually a better version of my question, so you nailed it, but I got another one. Actually, I have quite a few. But one that would interest me, because again, I'm a social scientist, so a lot of this I could track, but most of it was beyond. But what's interesting to me is this whole adaptive reinforcement learning is something that social scientists have been using with humans in terms of educational theory. And
that's where it comes from, exactly. Yeah.
And I'm curious, just the bigger picture is, it's so interesting that what you're trying to reproduce is a human response that works in the world our world, and you're trying to get these cells to do the same thing. And I
Yeah.
just think that parallel is insightful and interesting, and actually, both humans and, synthetic or whatever you
Yeah,
call
yeah,
this is the
organic,
same thing.
biohybrid,
Organic, thank
sure.
you. Yeah, I just add any reflections on that.
Yeah, absolutely. I think my design approach for these systems is bio-inspired, which I think is sort of a little bit, there's like a poetry to it that you're trying to build out of life using some of the same forces that shaped life through evolutionary processes in the first place. And so like humans are not born knowing how to do tasks. Animals are often not born. Well, some of them are, like, some animals are born, they can immediately walk, which is incredible. But many tasks, especially the tasks that we as humans hold as the thing that sort of separates us from many other animals, are learned. And so I think if we want to try to get robots to do things that are above and beyond, learning is probably a good way just to discover some of those policies. Okay, thank you all for your questions. All right.
So we're gonna change gears to the committee questions. So if you need to grab some more coffee or a snack or step out, now's a good time to do that. You're welcome to stick around. I am gonna stop the recording because this is the end of the public session.
Sure, yeah, that's great.
And then we usually take committee questions from the most external member first.